Hello students, welcome to Spectra Educational Academy. In this video, I am going to explain answers for long answer type questions in current electricity. Question is, state Kirchhoff laws for electrical network. Using these laws, deduce the condition for balancing in a Wheatstone bridge. Okay, so there are two Kirchhoff laws. The first one is called as Kirchhoff's first law. You can also call it as KCL, Kirchhoff's current law, or you can also call it as junction law. Yeah. So statement. The algebraic sum of currents, at any junction is equal to 0. So there is, in another way also you can give algebraic sum of the currents at any junction is equal to 0. Mathematically what you can write is this is I equal to 1 to n is equal to 0. So you can give another statement also. The sum of currents flowing towards the junction is equal to the sum of currents flowing away from the junction. So you can understand with the help of diagram is okay. So therefore, let us say I1 is the current flowing towards, maybe you can take the odd numbers. For example, you can understand with the help of diagram like this. Suppose let us say this is a point in any circuit. So this is a resistor. You can next when you can take like this, you can take like this, you can take like this, you can take like this. Take few of them. Okay, if you want, you can take all odd ones towards the junction. Suppose let us say this I1, I2 away, and I3 towards, I4 away, I5 towards, I6 away, I7 towards, I8 away. So it's your wish. You can take even numbers also towards. So even otherwise you take first 4 towards and next remaining 4 away. So there is no such restriction. So as per the diagram, what you can write is I1 plus I3 plus I5 plus I7. These are all currents flowing towards the junction. So the currents flowing away from the junction are I4, I6 and I8. So you can understand the statement with the help of diagram like this. Moving to the second statement, the algebraic sum of the potential differences. Algebraic sum of the potential differences around any closed or in any closed path, or you can say closed mesh is equal to 0. So you can write the potential difference in terms of current and resistance. Even potential difference sometimes can also be EMF. Algebraic sum of EMF is equal to 0. So before we apply second law to any circuit, we have to take the sign convention both for current and EMF. Suppose in a closed path, if you are moving from positive terminal to negative terminal of a battery, if you are moving from, if path is taken, the path is traversed, this is a sign convention for EMF and current. So whenever you apply Kirchhoff's second law, if path is traversed from positive terminal to negative terminal of a battery, then it should be considered as positive. Sorry, it should be considered as negative. EMF should be negative. Then if path is in opposite direction, if path is traversed from negative terminal to positive terminal of a battery, then EMF is positive. Negative to positive means EMF should be considered positive. Same way, if path is traversed in the direction of current in a closed loop or mesh, the corresponding potential difference, potential drop in particular, potential drop is negative. Potential drop is negative. If path is in the direction, potential drop is negative. If path is traversed in opposite direction of current, the corresponding potential drop is positive. So you can understand even like this also, this is the resistor. In case if you are taking in opposite direction of current, so potential drop is positive. Okay. So in the previous case, if you are moving in the direction of current, this is resistance. So potential drop is negative. So it should be minus IR. Here it should be plus IR. Okay. So let us try to apply these two Kirchhoff laws to obtain balancing condition of Wheatstone bridge. Okay. First, let us describe Wheatstone bridge. Wheatstone bridge works on the principle of Kirchhoff laws. Works on the principle of Kirchhoff's laws. It consists of four resistors P, Q, R and S arranged in a closed path, or you can say arranged in the form of quadrilateral. So like this. So you can understand with the help of diagram. So this is the sides of the quadrilateral. So in the sides of the quadrilateral, you can represent the resistors. So this is P. You can say this is Q. This is P. This is R. And this is S. So, okay, you take this is A. This is B. Between A to B, so looking at the diagram, you can frame the sentences. This is a plug key. Yeah. So you can frame the sentences. between A and B, a battery between A and B, a battery of EMF and a plug key is connected, and between the junctions C and D, a galvanometer between junctions C and D, a galvanometer of resistance G is connected. So hereafter you can proceed with the equation part. Yeah. So here at junction A, current splits into, so this is the main current. This main current splits into I1 and I2. So there is again one more split here. So Ig is the current flowing through galvanometer. And after that, this is going to be I3 and this is going to be I4. Now applying Kirchhoff's first law at junction C. Yeah. So I1 is the current flowing, that is equals to both I3 and Ig are flowing away. Call this equation 1. Similarly, applying first law at the junction D. So therefore, at junction D, both I2 and Ig are flowing towards D, and I4 is going away from D. So you call this equation 2. So this is the application of first law at junction C and D. Now, applying second law to the loop A, C, D, E. So as per sign convention, when you traverse in the direction of current, the corresponding potential difference is negative. So that is why the potential difference between A and B can be represented as I1 minus I1P, because potential drop is negative when you move in the direction of current, minus IgG. Even between C and D also you are moving in the direction of current, so therefore negative potential drop. But between D and A, you are moving against I2, so therefore corresponding potential difference is positive with R. So this is equal to 0. Similarly, applying second law to the loop C, B, D, C. So you are moving in the direction of I3. So potential drop between C and B is minus I3Q. From B to D, you are moving against I4. So therefore corresponding potential drop is positive, I4S. Between D and C, moving against Ig. So therefore corresponding potential drop is positive, Ig with capital G. Okay, so this is equation 2. So there is a condition called balancing condition. If galvanometer do not show any deflection, then bridge is said to be balanced. balanced. So therefore, Ig equal to 0. Putting this Ig in equation 1, 2, 3, and 4. So you call this is 3, you call this is 4. So putting Ig equal to 0 in equation 1, 2, 3, and 4. So first equation transferred as I1 equal to making Ig 0. So therefore you will get I3. Then similarly, second equation transferred as I2 equal to I4. So it means you can understand that in the diagram also, if Ig is inactive, I1 equal to I3, same current flows, because P and Q will be in series. Similarly, if Ig is inactive, I2 same current flows through even S also, because both R and S are in series. The next, same. So you call this is equation 5. You call this is equation 6. Similarly, substituting Ig in both the 3 and 4. So 3 transformed as minus I1P, minus I1P. This term will become 0. You will get minus I2R, minus cancel both sides. You call this is 6. Similarly, substituting Ig 0 in equation 4. So you'll get I3Q. So this term does not exist. So is equal to minus I4S. You call this is 7. So minus minus cancel. So dividing 6 and 7. Dividing 6 and 7. So I1P divided by I3Q is equal to I2R divided by I4S. Then, so in equation 5 and 6, we know that I1 equal to I3. So therefore, you can cancel I1 and I3 because they both are same. Also, I2 equal to I4 as per 6. So therefore, you can cancel both I2 and because they both are equal. So therefore, the balancing condition of Wheatstone bridge is P by Q is equal to R by S. So definitely you can expect a numerical for 2 marks based on this balancing condition that is already explained in the previous videos. Thank you very much, students, for watching my video. In the next session, I'll continue with another long answer type question in the same chapter. Thank you very much once again.